Hello again. In this video we are going to look at the concept, at the idea of what a rate of change is. And to give us an idea of what we're talking about, we're going to look at an example of temperature. So the table right here on the right shows the temperature T in Tucson, Arizona, little t hours after midnight. So what can we see over here? We see that at midnight the temperature is 85 degrees Fahrenheit, and at 3 a.m. the temperature is 76 degrees Fahrenheit, and at 4 a.m. the temperature is 7 degrees Fahrenheit. So it looks like it was still fairly hot at midnight, and then it cooled down. Now the question that we are being asked to answer is, when does the temperature decrease the fastest? Between midnight and 3 a.m. or between 3 a.m. and 4 a.m.? Let's make some space over here and let's investigate that question. So what happens between midnight and 3 a.m. if we are looking at this time interval from 0 to 3 a.m.? Well, the temperature went down, and it went down by 85 to 76, that is minus 9 degrees. So it went down by 9 degrees. And between 3 a.m. and 4 a.m., the temperature went down by 6 degrees Fahrenheit. So what can we say at this point? Well, we can say that the temperature went down more between 0 and 3 a.m., but did it go down faster or more slowly between those two times? That is the question right here. So let's look at those two time intervals. So a time interval we can describe in terms of our input variable t. So let's let t go from 0 to 3. 0 is less or equal to t is less or equal to 3. How did the temperature change? And temperature change, the variable for our temperature is capital T, and the sign for change in mathematics often is Greek delta, the capital letter delta. So delta T denotes the change in temperature in our example. And we already computed that was minus 9 degrees Fahrenheit. And we also already computed that for our second time interval. And let me get that right. That is from 3 to 4 a.m. There, delta T was minus 6 degrees Fahrenheit. Okay. Now those two time intervals are not created equal. One of them is way longer than the other. The first one is 3 hours, the second one is just 1 hour. So we use the same notation, delta little t, to denote the length of the time interval. And for our first time interval, that's 3 hours. And for our second time interval, it's only 1 hour. So we want to take that into consideration when we are answering this question about how fast did the temperature decrease. It decreased by 9 degrees Fahrenheit over an interval of 3 hours. We can compute that as a ratio and say, so we have a rate of temperature change, we have our temperature change divided by the time length that it took. That's minus 9 divided by 3. That is minus 3 degrees Fahrenheit per hour. So if the temperature dropped steadily during those 3 hours, then every hour we would have lost 3 degrees Fahrenheit. During the time from 3 to 4 a.m., what happened? Well, we had a 6 degree temperature change, but it only took 1 hour. So there we have minus 6 degrees Fahrenheit per hour. And that is a lot faster. So we can say that on average the temperature decreased at an average rate of only 3 degrees Fahrenheit per hour between midnight and 3 a.m., but it decreased at an average rate of 6 degrees Fahrenheit per hour between 3 and 4 a.m. So the average rate of change is what we are computing right here. So these are examples of average rates of change. And so to answer our question, 6 degree drop per hour is faster than a 3 degree drop per hour. So the winner is 3 to 4 a.m. We can also look at this graphically, and we can define technically this idea of average rate of change. So if we have an output Q and an input T, then the average rate of change, or just the rate of change of Q with respect to T, is given by the change in Q divided by the change in T. And using our delta notation, we say that is delta Q divided by delta T. And in general, when we have input and output variables, we think of the average rate of change as the change in output over the change in input, if you'd like to think about it this way. And that is what we can see over here. So if we have Q as a function of our input T, so that's what you see in our graph over here, then we can also interpret graphically this average rate of change. So our temperature probably didn't drop exactly 3 degrees every hour. It might have dropped more quickly at first and then more slowly later on. And so what we are computing is f of a right here, and f of b is this value right here. And when we are computing the change in Q over the change in T, we are really computing f of b minus f of a divided by b minus a. So right here, this distance is the change in T, and this distance is the change in Q. And so we see that we are computing is this vertical distance divided by this horizontal distance, and that is actually the slope of the line connecting the 2 points on the graph of our function. So this slope is our rate of change. And we can compute it in this way, right here. F of b minus f of a divided by b minus a. Let's put that down as an alternate formula for our rate of change. Actually, I have enough space right here. So we can say that the average rate of change of a function q equals f of t on the interval a less or equal to t less or equal to b is given by the formula f of b minus f of a divided by b minus a. And it's not a new formula, it's just a different way of writing the change in our output divided by the change in our input, either using our variables q and t, or we could also say this is a change in output divided by the change in input.